everyone. This is the second lecture of week 11. So, for the past 2 weeks and the first lecture in week 11, we have been discussing about linear program, right. And we have discussed two algorithms. One of them is the simplex method, and the other is affine scaling method, right. So, from this lecture onwards, we will learn about Karmaker's algorithm, okay, Karmaker's method. Okay. So, I had mentioned in passing about Karmaker's method in some of the previous lectures. So, if you recall, so this algorithm was given by Narendra Karmakar. So, he was graduate from IIT Bombay. He finished his BTech at IIT Bombay in 1978, right. So, so he gave this algorithm which you can say challenged the might of simplex algorithm. So, I mean, if you look at the history of the algorithms for linear program, Danzig came up with simplex method in 1946, okay, and the ellipsoid method was actually discovered later. The advantage of simplex method over the ellipsoid method, right. So, is because in practice simplex method was much faster for most of the practical linear programs, right, but in the worst case ellipsoid method was better. Okay. So, I mean, we have seen an example, a pathological example where simplex method actually takes 2 power n iterations, right. So, that is the worst case for simplex method, but ellipsoid method has a guarantee that for any linear program, okay, the number of iterations is polynomial in n, okay, polynomial in the number of variables, right. I mean, it does not blow up like 2 power n or anything of that sort. But people did not use ellipsoid method. I mean, when given a choice between simplex method and ellipsoid method, people were always using simplex method, because for most of the practical purposes simplex method was much faster than ellipsoid method. Okay. So, this was the case until Narendra Karmakar proposed this algorithm called the Karmaker's, which is popularly known as the Karmaker's method or Karmaker's algorithm, right. So, this again has the worst case guarantee of being polynomial in n, okay, and it performs better than ellipsoid method. So, in many of the practical cases Karmaker's algorithm was at least performing close to the complexity of the simplex method, or sometimes performing better also. Okay. So, you can say that people switch to different kinds of algorithms only after Karmaker's method was formulated in 1984, designed in 1984. Okay. So, just to give the timeline of how the algorithms came out. Okay. So, note that so first Danzig designed simplex algorithm or simplex method in 1946. Okay. So, it is quite old. Okay. And ellipsoid method, I do not recall the year, but was discovered much later, was designed much later. So, so if you compare simplex and ellipsoid methods, okay. So, ellipsoid method gives provides worst case guarantee, whereas simplex method was faster for most of the practical settings. So, people were always using simplex method. Okay. So, all this until Karmakar designed this method in 1984. Okay. So, this gives worst case guarantee, I should say a better worst case guarantee than the ellipsoid method. And performed either close to simplex method or sometimes better. Okay. So, yeah, this was clearly much better than the ellipsoid method, and so if you compare practical purposes, sometimes it was better than simplex, and even when simplex was better, Karmakar's was still performing close to what simplex would have given. Okay. So, in many of the places after Karmakar gave his algorithm, people started employing Karmakar's algorithm rather than simplex method, but yeah, simplex method still continues to be in use. Okay. So, now you must actually be asking about affine scaling method, right. So, I mean we skipped ellipsoid method because I mean nobody uses it now, I mean so yeah, because we have an algorithm that gives a better worst case guarantee, which is Karmakar's algorithm, and for even for practical purposes simplex method was much better. So, ellipsoid method is just I mean in the academic circles now. But yeah, affine scaling is something that people study widely even today. So, when was it discovered and what is its performance, right? So, affine scaling method is actually was discovered after Karmakar's algorithm. Okay. It is, you can say, a simplification of Karmakar's algorithm. Okay. Though I mean I have not read about worst case guarantees or anything of that sort for affine scaling method. Okay. So, Karmakar's algorithm comparatively is a little more difficult to understand. Okay. So, I mean affine scaling is you can say a simplified version which actually I mean helps us understand I mean how Karmakar's algorithm works. Okay. So, the intuition is much clearer with affine scaling method than with Karmakar's algorithm. So, that is the reason I first covered affine scaling method, so that you understand what is going on, and I will discuss Karmakar's algorithm as I mean I will first discuss the differences between affine scaling method and Karmakar's algorithm before actually discussing the algorithm in detail. Okay. All right. So, yeah, I will also write this down that yeah. So, affine scaling method is a simplified version of Karmakar's method or Karmakar's algorithm. Designed in 1985. Okay. So, the simplification was because I mean this gives a better intuition of what is actually happening than Karmakar's method. So, yeah, gives a better intuition to understand the algorithm. Okay. Fine. So, that is roughly what is about Karmaker's algorithm. I wanted to discuss this since learning different kinds of algorithms, and I mean we need at least a rough comparison between these algorithms so that you understand which one to use when you actually are facing a problem in a practical setting, an optimization problem, a linear programming problem in a practical setting. Okay. Alright, so let us start with the differences between Karmaker's algorithm and affine scaling method. Okay. So, affine scaling method okay. So, yeah, you can recall that in affine scaling method we convert the given problem into the standard form, right. So, yeah, I think that was the first step. So, you can see the first step is just to convert the given LP to its standard form, right. So, that is how affine scaling method starts, right. But here you convert it into a slightly different form, which Karmaker calls it as the canonical form. Okay. So, I will tell you what a canonical form is. So, but before that, I mean just to put things in perspective, yeah, the form that you convert in affine scaling method is the standard form, that is minimize C transpose x subject to Ax equal to b, x greater than or equal to 0, right. But here you convert it into a slightly different form called as the canonical form. Okay. So, that is the first difference. Okay. And if you recall what you do in affine scaling, right. So, you first center the initial point or whatever point you have, then you find the descent direction and project it onto the feasible set, and yeah, I mean you move over there, right, and then decenter it, right. So, that is the procedure, right. So, I mean that is something that you recall this, right. Yeah, this first step is the centering process. The second step is you find the direction and move over there, and the third step is decentering process, right. So, yeah, this is the formal algorithm. So, if you recall the steps, yeah, this was centering. The first step is centering, second is moving along a direction, and third is decentering, right. Yeah, the other thing that you have to see is the centering process actually uses a linear transformation, right. So, multiplying with a matrix, right. So, that is actually you use a linear transformation, right. And the decentering process also uses another linear transformation, you can call it the reverse linear transformation, but nevertheless both are linear transformations, right. So, but here what you use is actually called as a projective transformation and not linear transformation. Okay. So, centering occurs via a linear transformation and decentering via a reverse linear transformation, right. Here centering actually occurs via a projective transformation. Okay. Centering via a projective transformation and decentering via a reverse projective transformation. Again, you may not immediately understand what is a projective transformation, right. but nevertheless, I mean, I would like to indicate all of this before going into the method, because without this you may not understand what is going on at all, right. So, basically you can say that these are the differences between a fine scaling method and Karmaker's method, okay. So, where instead of standard form you convert it into a canonical form, and instead of linear transformation and reverse linear transformations you use a projective transformation and a reverse projective transformation. And yeah, so based on this there are other issues that you have to handle. So, the other differences come because of these two differences. Let us get started with the method now, given that I have given an overview of the Karmaker's method, right. So, first let me describe the canonical form, okay. So, linear program is said to be in its canonical form when you are minimizing C transpose x subject to conditions that A x is equal to 0, A transpose x equal to 1 and x greater than or equal to 0. Okay. So, you can see that it is slightly different from the standard form, right. So, the standard form, if you recall, is of the form min C transpose x with respect to x, subject to the conditions that Ax is equal to b and x greater than or equal to 0, right. So, here you can see that there is a small change. Instead of Ax is equal to b, you have Ax equal to 0 and A transpose x is equal to 1, okay. And yeah, so the other conditions are there anyway, where you have A is an m cross n matrix with rank m, okay. This is not the binding condition. The binding condition is that the solution of this problem should actually, or rather not the solution, the optimal value of the objective function should be 0, okay. So, yeah, the optimal value, which is C transpose x star, should be equal to 0, okay. So, yeah, that actually is a more binding constraint in the canonical form, okay. The other ones are much simpler, I mean it is handleable, okay, but this condition that the optimal value C transpose x star should be equal to 0. So, what it says is that you must actually know the answer in some sense, right. So, if you do not know the answer, in the sense know the optimal value. So, yeah, you may not know the solution x star, okay, but you must know that you substitute the solution, the optimal value of the objective function should go to 0, should be actually equal to 0, okay. So, that is the canonical form that Karmaker's algorithm asks for, okay. So, now let us actually try and understand how to convert a given problem to satisfy all of these conditions, okay. Alright. So, yeah, suppose you are given a linear program in general form, right. So, yeah, if you are given in general form, it will be of this form, where you have min C transpose x subject to say A bar x less than or equal to B bar and A tilde x equal to B tilde, right. So, that is the very general form. You know how to convert this into standard form, which is of the following form, where you have min C transpose x subject to yeah, this C and this C could be different. So, let me actually call this as C hat or something, okay. So, this will be of the form A x equal to b and x greater than or equal to 0, right. So, this is the standard form with, yeah, so A is m cross n matrix with rank of A equal to m, okay, fine. Now, how do I convert this into what is called as the canonical form, right. So, I am just going to introduce one more variable, right. So, let us say this is assume that now it is in standard form. I am just going to discuss about converting a problem in standard form to a problem in canonical form. So, okay. So, yeah, so if this is of the form let us say, so you are minimizing C1 x1 plus C2 x2 and so on, right. So, C1 x1 plus dot 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 plus Cn xn. Okay. So, what I am going to do is, yeah, I am actually going to introduce a new variable, okay, xn plus 1, okay, and I am going to fix that to be equal to 1. Okay. So, possibly I will write down the form and then explain how yeah, both of them are equivalent. Okay. Okay. So, I am claiming that the canonical form that I have written here, okay, and sorry, yeah, the standard form that I have written here and the canonical form that I have written here are both equivalent. Why is that the case? So, note that I have introduced a constraint xn plus 1 equal to 1. Okay. So, that means, so the constraint here can actually be written as Ax minus b equal to 0, which is nothing but Ax equal to b, right, and xn plus 1 equal to 1 means that xn plus 1 greater than or equal to 0 is a redundant constraint, but that is okay because we want it in the form that we are looking forward to, right. So, that is the reason I have written xn plus 1 greater than or equal to 0 anyway. Okay. And I have also included this part minus V star xn plus 1, where V star is actually the solution of, sorry, the optimal value of the objective function of the standard form, optimal value of the standard form. Okay. Okay. So, if yeah, xn plus 1 equal to 1, then the optimal value of the objective function here will be actually equal to 0, right. So, yeah, that is the reason how the problem written in the standard form and the problem that I have written in the canonical form are both equivalent, right. And you can see that it is clearly in the canonical form because, yeah, this is a problem in n plus 1 variables, right, and it is of the form, the first constraint that I have written is of the form Ax equal to b, Ax equal to 0, sorry. Okay. Just that the new matrix now, so I mean you can write that as, let us say, A hat x equal to 0, where A hat is A and minus b, you augment minus b with A, right, and you also have an A transpose x is equal to 1, where A is, you have 0 0 0 0 n times and a 1. Okay. So, yeah, that will give you xn plus 1 equal to 1, A transpose x equal to 1, and of course, x is greater than or equal to 0. Okay. So, this is clearly in the canonical form, and yeah, the problem given in the standard form and the problem given in the canonical form are both equivalent to one another, right. So, any given LP can actually be converted into a canonical form. You can see that just from this. What you are going to do is just that you first convert it into standard form, okay, and add a dummy variable xn plus 1 equal to 1, and then I mean do this simple conversion that instead of Ax equal to b, you write Ax minus b into xn plus 1 equal to 0, and the objective function is C transpose x minus V star xn plus 1, where V star was the optimal value of the standard form. Okay. So, the canonical form is very, very clear, right. But let me tell you, there is a catch. Okay. The catch is actually with V star, right. So, you do not know V star in general, right. So, I mean given linear program in standard form, it is not that some genie comes and gives us see this is the optimal value V star, optimal value of the objective function, right. So, that never happens. So, it is, I mean you can write this when you know V star, right. If you do not know V star, you cannot write this, is not it. that is correct, but yeah, we will take care of that as we go along, okay. But this is the way you first convert it into canonical form. We will now go ahead to the next step, okay. So, we have converted the given problem to the canonical form. Now, how do we do the centering, decentering and all that, right. So, that is something we will go ahead with at this point. So, fine, yeah. So, this is done. Instead of converting it to standard form, we have converted it into canonical form. Now, the next step is to take an initial point and do centering, but not using this linear transformation, but using a projective transformation. Okay. So, let us do that, but before that I will have to tell you what a projective transformation is. Okay. So, assume that the transformation is given by the following equation. So, before that, capital X is the diagonal of X, right, and yeah, Y is given by X inverse X by 1 transpose X inverse X. Please recall that 1 is a vector of all ones, okay. So, this is the projective transformation, right. So, this is slightly different from the linear transformation, which was just capital X inverse X, right. So, that was something we saw here, yeah. So, you can recall that Yk is just Xk inverse Xk. So, similarly here, yeah. So, if Xk, capital Xk is diagonal of Xk, then Yk is Xk inverse Xk, and this is capital Xk inverse Xk, okay. So, this is yeah. So, something that is very clear is that 1 transpose Yk is actually equal to 1, right. So, that is because, yeah. So, just put 1 transpose, you cancel and you get 1, right. So, that is so simple as that, okay. Now, how do you get back Xk, little xk from little Yk, right. So, that is also important, we will derive that now, okay. So, note that capital Xk Yk is Xk by 1 transpose Xk inverse Xk, right. So, that implies that Xk is actually capital Xk Yk by 1 transpose Xk inverse Xk, right. So, yeah, but this is not complete because this depends on Xk. So, we will correct this shortly. So, note that A transpose Xk should be 1, right. So, that is coming from this constraint, right. So, A transpose Xk is 1, okay. So, that means, what that means is that 1 equals A transpose Xk Yk by 1 transpose Xk inverse Xk, right. So, that implies that A transpose Xk Yk is 1 transpose Xk inverse Xk, right. So, I can replace 1 transpose Xk inverse Xk by A transpose capital Xk Yk, right, and because of which we actually have yeah. So, I will write it here. It turns out that Xk is Xk Yk, capital Xk Yk by A transpose capital Xk Yk, okay. So, yeah, so this is the projective transformation by which X is converted to Y, and this is the reverse projective transformation where Y is converted to X, okay. So, what we have seen until now in Karmakar's method is we saw how to convert a given LP into the canonical form, right, and then we have also learnt what is projective transformation. So, we will shortly in fact, I mean we will actually write down the algorithm properly in the next lecture. Okay. Thank you.